Here are the answers to the synthesis problems on the practice final exam worksheet. Remember, our first question whenever we're doing synthesis is, does the carbon skeleton change or does the functional group change? Sometimes both will change, but oftentimes it's one or the other. And if we number the carbons here, we observe that we've added 2 carbons to the end of this alkene. And we don't know how to add carbons, basically, removing a hydrogen like that. But we can add carbons to an alkyne. So we know how to deprotonate the alkyne and add carbons. So in this case, we just need 2 carbons. And that will get us to an alkyne that has an additional 2 carbon group on it. And we know how to get from that alkyne to this alkene. Sodium in liquid ammonia will take this alkyne and turn it into the transalkene. And of course, sodium amide plus the ethyl chloride will take this alkyne and add the extra 2 carbon group. So then the question becomes, how do we take this 5 carbon alkene starting material and turn it into the alkyne? Well, we know a reaction that can, or a sequence at least, that can turn alkenes into alkynes. If we add Br2 to this, we get the dibromide. And then if we add excess NaNH2, we can do a double elimination to create the 2 new pi bonds. You might observe, and I think actually the book says we need to quench with water, so that's fine there. You might observe that this reagent here used to deprotonate the end of the alkyne, and this reagent here used to create the alkyne are the same ones. So in theory, if we didn't add water, we wouldn't quench the anion that's formed here after adding excess NaNH2. We wouldn't need this NaNH2, and we could take the anion and add it directly to the electrophile. So that's possible if you want to get rid of these 2 extra sort of steps. But if you had it exactly like I had in green, that's also no problem. If we look at the next reaction, we see 5 total carbons, and we also had 5 carbons right here with our alkene. And so we're not actually adding or subtracting carbons, we're simply, looks like we're cutting a 5 carbon chain in half, and we know how to do that with ozone, and these are both aldehydes, so that's DMS. If they were carboxylic acids, it would be water that we'd use as our second step. And so there is the alkene that we want. We could actually use the cis version of this alkene too. That's not important in this case because we can't really tell what the stereochemistry was after we cleave it. So how do we create this alkene from our original 5 carbon alkene? Well, we just simply need to migrate this double bond down the chain, just like we learned in chapter 9. So if we add HBr in a Markovnikov addition, we end up with this leaving group on the 2nd carbon, and of course we can do a Zaitsev elimination using ethoxide. We can remove this hydrogen and create the internal alkene right here that we can then cleave. So this is a nice little 3-step process to make these 2 aldehydes. Let's look at this reaction up here. We're taking this tertiary alcohol and we're converting it into, it looks like an alkene that's sort of migrated itself around the ring. And of course we can create alkenes through elimination, and I think in this case I'm going to move this one down just a little bit, get it out of the way there. In this case I think we're going to want our elimination to occur from a leaving group right here, because that is closer to what we started with, right? This leaving group here is now getting us closer to the functional group that we had in the original structure. And we can even get closer by adding HBr to this alkene, right? So we can use this alkene here, add HBr. We'd have to use peroxides because we want to add that in a anti-Markovnikov fashion. And then to do this elimination, we'd have to use a large bulky base so that we can at least favor this less substituted alkene. and you can even make your base bulkier if you wish. But here HBr and peroxides can react with this alkene, and I think straight out of our lab manual we can simply dehydrate this and get the more substituted alkene as the thermodynamic product just by adding a little bit of acid and then undergoing the E1 type mechanism that we explored in experiment 6 in our lab. Okay, so this fourth one on this page has a number of 6-membered rings and what looks like some other interesting stereochemistry here. So of course our functional group is located at the top carbon of this ring, and it almost looks like we just added an OH to the right side of the ring. I'm not really sure how we could do that, but if we observe that there's an OH and a bromine that are in an anti-relationship, I think it's certainly possible that we could take this alkene and add Br2 and water to it in a halohydration reaction. I think that's the right name for it. But of course we're going to put the water on the more substituted carbon, so the OH forms here with this blue dot, and that's where we see it form in our two products. And there's really no control over the face of the alkene, so we're going to get the bromine up and the OH down, or the bromine down and the OH up. This is a poorly drawn OH here. We'll fix that a little bit. And so I think this alkene will give us both of these diastereomers undergoing this reaction with bromine and water. So now the question is, how do I make this alkene from the starting material bromide? It looks like it's just a simple elimination reaction, and if we look more carefully at the hydrogens, I think we can influence the outcome here because this hydrogen is anti-paraplanar to the bromine. And so it's well set up for a nice elimination, and we can do that with simply some ethoxide as our base. It'll remove that H, not the other H, not the leftmost H, and will give us this alkene almost preferentially. So really that's only 2 steps. Eliminate and then add, and it looks like it's really complicated because we're essentially changing this H into an OH. That's the overall effect of this, but it's a bit more simpler than that when we consider that this bromine here is not the same as this bromine there. Alright, so the next set, here we have a tosylate. There are 5 carbons here, and there are 5 plus 2. So somehow we need to add this group to the end of our 5-carbon chain, because I think we can assume that this chain of carbons here is the same 5-carbon chain we start with. So the question becomes, how do I put ethoxy on the end of the chain at carbon number 5? And that's you might think of it as adding ethanol in an anti-Markovnikov fashion. I think I'm going to think of it as maybe the ethoxy is a nucleophile, and if I just hang a leaving group right here, essentially, I'm ready to bring in ethoxy and just do the reaction. So how do we get a leaving group there? Well, a large base will give us the less substituted alkene, and HBr and peroxides is our typical, and that gives us the leaving group right there. And I think one more step really, all we need is ethoxide. So this is a primary, this is a strong base, strong nucleophile, and we know that that combination results in a major product of SN2. And so we're going to substitute ethoxy for the bromine, and that's what you get. So here we see what might look like a really strange product is really just the result of a simple SN2 reaction. Another option would be to use hydroboration, oxidation. You can fill in the other reagents. There's of course 2 steps here, and we can get to here, and then we can somehow add ethyl chloride as an electrophile here. Now this reaction probably won't work so well. If we could somehow remove this H, that would work better. So this is probably not the way we want to go, at least in our class. We'll learn a bit more skills in this department next semester. So let's not use that, but that's maybe a thought you might have had, and it would work given just a little bit more information. Here, the bottom one, we have 5 carbons in our alkyne, and then we have 7 carbons here. So it looks like we need to add some carbons, and if we count, looks like between 4 and 5 we have some functional groups, right? We have this syn dihydroxylation, and we can predict that OSO4 gives us a nice syn addition to this alkene. And I think it's NaHSO3 here to work it up, maybe some water. You'll have to look that up actually. I'm more concerned with the osmium tetroxide here. I think I'd be happy if you just showed me what the osmium, use the osmium as your final step. So now we have a 7 carbon alkene, and of course we need to add 2 carbons. It's probably a good assumption that those are the 2 carbons we need to add. We know how to add carbons. First step, just deprotonation. Second step, 2 carbon addition, and we end up with that. And of course it's easy to get to the trans alkene here, Na solid in liquid ammonia. This is a comma. It's supposed to be a comma. Doesn't look like a comma. It's supposed to be a comma there. And so that's the reagent we need to make this trans alkene, and then osmium tetroxide gives us the 2 OHs. So that's another little simple 3-step transformation. Let's look up at the top right. We have 5 carbons to start with, and we have 7 carbons to end with. It's almost like the previous one where we had to add 2 carbons, and I bet you we'll use the same technique, although now we're starting with this dibromide compound, and we know that we could undergo a double elimination to make an alkyne, and of course we know that we need an alkyne in order to add 2 carbons, and of course an alkyne or an alkene can certainly be turned into this alkane with relative ease. So we're going to have some sort of double bond or triple bond that gets hydrogenated at some point, and we're not going to worry about that right now. We've used this so many times, hopefully you're familiar with it. That's going to add 2 carbons for us. Apparently when I wrote this practice problem set, I really liked 7 carbons, and I really liked this setup here. So now we have 1, 2, 3, 4, 5, 6, 7. Good, I have my correct number of carbons. I've added 2 more, and if we just use H2 and palladium, we can hydrogenate the triple bond all the way down to the single bond, and that's basically it. So we need to create a triple bond using those 2 bromines to create the terminal alkyne, deprotonate, add 2 carbons via an SN2 reaction, and then hydrogenate the triple bond. In this case we have 5 carbons across. We have 2 more as these are random methyl groups. Here we have 7 carbons in the main chain, and so we need to add 2, probably these 2, because we see that this T-butyl group kind of gives us a handle or a landmark, if you will. And so we need to add 2 more carbons, and then end up with a methyl ketone. And we know that mercury sulfate and water and sulfuric acid and a terminal alkyne can give us that methyl ketone. So this seems like a reasonable intermediate here. Once I've established that, if I look at this 5 carbon piece right here, that's probably this 5 carbon piece right here. Actually it's a 7 carbon piece, but you get the idea. It's a 5 carbon chain, and thus I have a 2 carbon alkyne that I need to add. So maybe I need to add that alkyne as the nucleophile, as an alkyne, like we saw in class. So maybe we bring in this anion to react with a certain primary halide, right? So we can use this alkyne as an anion to react with the primary halide, and that should get us to this alkyne at the end. So we can turn alkenes into terminal alkynes via adding 2 carbons, simply by turning that alkene into an alkyl halide. We want a good leaving group. We prefer that it's primary. That makes it for an easier substitution. So here we take our alkene, we give it a primary, turn it into a primary leaving group through anti-Markovnikov addition of HBr, and then we use a acetylide anion to extend the chain by 2 and leave us with the alkyne, and then that can be converted into the ketone. We can make a methyl ketone on this carbon right here via sulfuric acid, mercury sulfate, and water. So again, this is a little 3-step sequence. It looks a bit more complicated at first, I think, but if we think of sort of the reverse reactivity, if you will, we're used to making alkynes, deprotonating them, and then bringing in the electrophile. But why can't we make the electrophile and then bring in the deprotonated alkyne? That's perfectly reasonable to do. So don't forget about that as a valid technique for extending the chain of really any sort of organic compound that can be created or turned into this primary halide.